Okay, picture this. You're sitting at the airport terminal, looking out the window, and you see this absolute behemoth of an airliner rolling by. I mean, we're talking upwards of 700,000 pounds of metal, fuel, and passengers. And you just kind of have to wonder, how on earth does that thing gracefully lift off the runway and absolutely hurtle through the sky at 80% the speed of sound? Honestly, it almost seems like magic, right? But the secret lies right there in those brilliant roaring metal cylinders hanging right beneath the wings.
Welcome to This Explainer. Today, we are going to completely demystify the modern jet engine, and I am so incredibly excited to take you on this journey. We're going to take some seriously complex engineering and break it down into super simple, logical concepts. No dry textbook jargon here, I promise. Just the fascinating, real-world story of exactly how human ingenuity managed to conquer the skies.
So here is our flight plan for This Explainer. First, we'll cover the basics of jet propulsion, then we'll take a journey straight through the engine's core. After that, we'll look at creating massive forward thrust, compare older turbojets versus modern turbofans, go over some real-world applications, myths, and facts, and finally, do a quick engine recap. Let's jump right into part 1, the basics of jet propulsion, fundamental physics. You know, before we even look at the machinery itself, we really need to understand the simple rule of the universe that makes all of this flight possible. And for that, we have to thank Sir Isaac Newton, who actually figured this out centuries before the very first airplane ever took flight. His third law of motion states that for every action, there's an equal and opposite reaction. So what does this actually mean for us? Well, a jet engine is basically just a machine designed to grab a bunch of air and throw it backward as forcefully and as fast as possible. Because that air is pushed backward, the airplane itself gets pushed forward. It is literally the exact same concept as blowing up a balloon, letting it go, and watching it zip crazily across the living room.
Now, to get that massive backward flow of air, jet engines rely on something called the gas turbine cycle. And honestly, you can just remember it with 4 simple, punchy words: suck, squeeze, bang, and blow. In your standard car engine, these 4 steps happen one right after another inside a single cylinder. But in a jet engine, they're happening continuously at the exact same time, just in different physical sections of the engine. It's a real game changer.
Which brings us to section 2, journey through the core, inside the engine. Okay, let's dive into the actual hardware. I want you to imagine we are a single stream of air, just about to be sucked into a jet engine during takeoff. Let's trace our physical path from the very front, all the way out the back. Our journey kicks off right here at the intake's front fan, which is made of these highly durable titanium blades. This massive fan literally sucks tremendous quantities of air into the engine. But watch closely. Notice how the incoming air actually splits. A portion of it goes straight into the very center, the core. But a huge portion actually bypasses the core entirely, just flowing around the outside through this duct. Keep that bypass air in the back of your mind because we're going to come back to it. For now, let's just follow the air that went straight into the core. So, that core air immediately slams into the compressor. This section is essentially made up of alternating rows of spinning blades and stationary airfoils called stator vanes. The spinning blades force the incoming air into a chamber that just gets narrower and narrower and narrower, while those stationary vanes straighten out the airflow. Because that space is shrinking, the air is being violently squeezed. It's a brilliant process that converts all the rotational energy from those spinning blades into just extreme static pressure. Right, so once the air is heavily compressed, it gets shoved into the combustor. This is the bang part of our cycle. Here, that highly pressurized air gets mixed with jet fuel and ignited. And the environment inside this combustion chamber, it is absolutely mind-blowing. The flame temperatures reach over 3,500 degrees Fahrenheit. That's about 1930 degrees Celsius. To put that into perspective, that is actually hotter than the metal engine parts themselves can technically endure. No way, right? So engineers actually have to carefully route cooler air from the compressor around the liner just to keep the metal from literally melting into a puddle. And this graph brilliantly illustrates those extremes mapped out across the engine stages. Check out that dashed line representing the pressure. See how it climbs so steeply as the air moves through the compressor? Then, look at the solid black line for the temperature. It absolutely skyrockets the second that air hits the combustion section. So what we've done here is create an incredibly energetic, incredibly high pressure, insanely hot stream of gas.
Moving right along to section 3, creating massive forward thrust, converting heat to force. So, we've got all this intense heat and pressure trapped inside a metal tube. How exactly do we convert that into the actual force that pushes our 700,000-pound airplane across the sky?
Well, those superheated exhaust gases desperately want to expand and escape out the back. But before they leave, they have to pass through the turbine. You can think of the turbine as basically a windmill facing a Category 5 hurricane. As these fiery, high-speed gases blast past the turbine blades, they force the turbine to spin at just incredible speeds. And here is the absolute genius part of the whole shebang. The turbine is physically connected to a central shaft that runs all the way back to the front of the engine. So by spinning the turbine, the engine powers its own compressor and front fan. It creates this beautiful, continuous, self-sustaining loop. Finally, after turning that turbine, the remaining hot gases shoot out the back through a converging duct called the exhaust nozzle. This nozzle accelerates the gas one last time, and this is exactly where Newton's third law comes back into play. This violently fast jet of hot gas shooting out the back, that's our action. And the forward thrust pushing the airplane, that's our equal and opposite reaction. Now for Section 4. Turbojets versus modern turbofans. Comparing engine types. Let's see how these basics evolved into the massive power plants we actually see on modern wingtips today. Because, well, early jet engines and modern ones handle thrust a little bit differently. So, the earliest jet engines were called turbojets. In a turbojet, 100% of the air sucked into the inlet goes straight through that fiery core we just talked about. All the thrust comes from the hot exhaust. But today, almost all commercial airliners use what's called a turbofan. Remember that huge front fan and the bypass air I told you to keep in mind earlier? Well, in a turbofan, only a fraction of the air actually goes into the core to keep the engine running. The vast majority of the air is just pushed by that giant fan completely around the core. And surprisingly enough, the sheer volume of thrust is actually provided by that cool bypass air. You know, you might think all the power comes from the fiery exhaust shooting out the back, but in a high bypass turbofan engine, that cool air flowing around the outside produces the vast majority of the engine's thrust. This design is just so much more fuel efficient at cruising speeds, and as a massive bonus, that cooler bypass air actually wraps around the hot exhaust, making the engine significantly quieter for everyone.
Let's head into Section 5, Applications, Myths, and Facts, Real-World Uses. Now that we've got the mechanics down, let's shift gears a bit. We'll look at where this tech is used out in the wild and clear up a couple of very common misunderstandings.
The fundamental gas turbine cycle we've been exploring is just incredibly versatile. I mean, you'll find variations of these engines powering daily commercial airliners, high-speed military fighter jets, massive cargo transport aircraft, and even unmanned aerial vehicles and cruise missiles. Whether it's a turbofan prioritizing fuel efficiency or a turbojet prioritizing pure supersonic speed, the core concept remains exactly the same.
Okay, let's bust a few myths here. First, as we just learned, the idea that a commercial jet flies solely by shooting fire out the back? Total myth. Most of the thrust is really just cold air being shoved backward by a giant fan. Second, you know how a car's spark plugs fire continuously while you drive? Jet engines have igniter plugs too, but they're literally only used to start the engine. Once that raging 3,500-degree fire is lit, it just sustains itself continuously, so long as fuel and air keep flowing. And third, just as a reminder, the whole engine is a brilliant continuous loop. The exhaust powers the turbine powers the compressor, and the compressor feeds the exhaust.
I absolutely love this quote from Animagraph's analysis of jet engines because it really perfectly demystifies the whole machine. Quote, "The turbofan can be thought of as a high-tech propeller inside of a duct, driven by a gas generator." Think about that. When you look at an engine on a Boeing or an Airbus, that giant spinning fan you see at the front really is just a highly advanced propeller. That fiery, incredibly complex jet engine hiding behind it, it's simply there to spin it. Finally, Section 6, a quick engine recap, bringing it all together. We've covered a ton of ground today, from Isaac Newton all the way to extreme thermodynamics. Let's quickly bring all these mechanical pieces back together for a final review.
So here is the full life cycle of a single breath of air entering a jet engine. Step 1, the massive titanium front fan sucks in huge amounts of air. Step 2, the compressor forcefully squeezes that air, drastically raising its pressure and temperature. Step 3, the combustor injects fuel, creating a continuous, raging fire. Step 4, those hot, expanding gases spin the turbine, which is physically connected to the front fan to keep the whole process going. And Step 5, the exhaust and bypass air shoot out the back, providing that equal and opposite reaction that pushes the whole aircraft forward. Suck, squeeze, bang, blow. It's really that simple.
You know, it is truly staggering to think about the sheer brilliance of the engineering that allows us to just sit back, sip coffee in a pressurized cabin while thousands of tiny controlled explosions are happening every single second just outside our window.